Hello, in this video we're going to talk about electrolysis. And so, what is that? Electrolysis is the process in which you can make a non-spontaneous reaction go. Or another way to think of it is that you could take a spontaneous reaction and run it backwards. So here's an example. It's very much spontaneous to take chlorine gas and sodium solid and turn them into sodium chloride. If you were to do this in an electrochemical cell, you would have a very positive voltage, which means this is very spontaneous. This is not a surprise. Now you want the non-spontaneous version of this. Well, you'd run it backwards. You take the chloride ion, the sodium ion, and you'd make solid sodium and chlorine gas. And this is a very non-spontaneous process with a very negative E0 cell. But with the magic of electrolysis, you can make this happen. So if you had some molten sodium chloride and you put something over 4 volts into this, you would probably need like 5 or 6 or 7 volts, or heck, maybe even more to make sure this really goes. But in theory, anything over 4.07 volts will make this reaction run backwards. You just apply this voltage to it with a decent amount of current, and you'll have chlorine gas come out the anode, you'll have liquid sodium come out the cathode, and that's how it works. So this is how many of our metals are made, right? Like if you wanted sodium metal to buy from the chemical store, it will be made this way. Michael Faraday is quite famous for discovering a bunch of elements, and Humphrey Davy, who came before him, because they discovered electrolysis. And so suddenly they could isolate all these metals that you couldn't isolate before. You could also do this with water. The oxidation and reduction reactions are listed here. This is just the standard hydrogen electrode, so it's 0 volts. And the overall E cell is negative, 1.23 volts, so it's non-spontaneous. But if you want to run this reaction, well, if you put more than 1.23 volts, then it'll go, and you'll make hydrogen gas and oxygen gas. Fun fact is that you'll make twice as much hydrogen gas as oxygen gas, because that's the stoichiometry of the reaction. That's kind of cool. Okay, so that's electrolysis. So the next thing we want to do is figure out how to calculate quantities related to electrolysis. And by doing so, you'll learn how this process works even better. And I think that educational goal is worth it. So I kind of wrote this as a bidirectional process. You can go between any one of these boxes as long as you follow the path. And so if you have current, how long you do the electrolysis and what current you put in, right? Time, how long you run it, current. You can use the fact that a coulomb is equal to an amp per second, or that we define an amp as coulombs per second, either one, and use those to find the charge, right? Because current is just defined as how much charge do you move per time. So you can use this to find charge. And then Faraday's constant tells us the charge on a mole of electrons. So you can go from the charge and find how many moles of electrons you have. Then once you know moles of electrons, you can look at the half reaction that interests you, say for sodium or for chlorine or what have you. And for example, every sodium needs 1 electron. If you're doing calcium, it's 2+, it needs 2 electrons. And so then you can go to the mole of, say, the sodium, the chloride, the calcium, whatever. And then from there you can use molar mass to get grams, or if it's a gas, you can use volume, etc. to get liters of gas, things like that. So let's practice this. So we got some calcium, and we're trying to make it from molten calcium chloride by electrolysis. So you have a current and you have a time. Those are the two things you need. And so the reaction will look a little something like this. You don't actually need this to do the problem, but I want to show it. Right, and so at your anode, you have the chloride ions going to chlorine gas. At your cathode, the calcium ions are turning into solid calcium. This is the one we want, but I mean, you need both because it's a redox reaction, so you need both parts. Your overall reaction looks like this. And the calcium and chloride are not aqueous because this is crazy hot and you actually have liquid calcium chloride. Now the thing you actually need is to know that every calcium has 2 electrons, because we're going to use this stoichiometric ratio in our problem. And so you start with the current and then the time. And so I replaced amps with coulombs per second, because that's the definition of an amp. And then time. Now we need to get this into seconds, and you have hours. So if you multiply hours by 60, you get minutes. If you multiply minutes by 60, you get seconds. 60 times 60 is 3,600. And then now we have charge after taking the current and time. So then we'll use Faraday's constant to find the charge on a mole of electrons. Then we use this mole ratio that we just put on the top. And let's make sure everything cancels. So the hours cancel, the seconds cancel, the coulombs cancel, the moles of electrons cancel, and we're left with moles of calcium. And then this question's a little vague as to whether it wants just moles or whatnot. So if this is on a test, you just give me moles, and I couldn't argue with it. But if you want grams, you can use the molar mass, and you can find that too. All right, so let's do this now the other way. Let's start from amount of metal and go back to current and time. And so here's the equations you're going to need. You're going to need the molar mass of aluminum too. So the first thing we need is the cathode reaction, and really all we need to know out of this is that there's 3 electrons per aluminum, which you could figure out by looking at the periodic table, right? Because aluminum only has one oxidation state, and it's going to be +3, so you can figure that out. So the first thing we need to do is find how much charge is needed to make this much solid aluminum. And so here's the aluminum we're starting with, and we'll convert it to moles. And then here's the mole ratio I just talked about, and so we'll use that. Moles of aluminum, or aluminium as they say in British English. All right, this is your moles of electrons, that's great. Then now your moles of electrons that you need to put into this to do the reduction, you can multiply that by Faraday's constant, you can find the charge on this number of electrons. All right, so we'll need to use that charge in the next step. We need to find how long it takes to deliver this amount of charge. And that you have to deal with the definition of current and how these are all related to each other. And so you can rearrange this equation. Coulombs over amps gives you time. And so we'll do that. And we'll plug the coulombs in here, divide it by amps, and we get the seconds it takes to deliver that amount of charge when you're going at 2 coulombs per second. All right, so now, again, this problem didn't specify how it wants time. So this would be a valid answer. That said, you should be a nice human and just convert it to hours. Right? Because nobody says 4 times 10 to the 5 second. You're going to say, oh yeah, it's 120 hours, because that's a normal way to talk. You could even put it into days if you want. And so the math to do that is here. Notice we don't give you these conversions on tests. You should know them. All right, that's all I have for this video, and thank you for watching.